So let's talk about this Cayley-Hamilton theorem. So the way to understand polynomials, it's to understand matrices using polynomials. Okay? Matrices via polynomials. Right? And this culminates in at least one place is what is called the Jordan canonical form. Okay, but that right. So we start with. No, I don't need to say all that now. So I'll just start with this side. So start with the matrix A in MNR. Any fields, I'll just write F. Okay, I'm not writing N. Okay. Field. Right? If any terminology is not fine, then you should just tell me immediately. Start with the square matrix. Starting with square matrix like this, and then the idea is to prove. Okay, the idea is to prove that there exists a polynomial Px in Fx such that P of A is equal to 0. This is not the goal actually, because this is actually very simple. So first of all, maybe I should explain what is this. Okay. So first of all, this 0 right here is a matrix, is an n by n, is an n by n matrix. What is P of A? I can say it, one can say it formally using homomorphism and things like that, but informally it is something like this. And I think this is all I will need to say. For example, you have x square plus x plus 1, then P of A would be but now these are not numbers anymore, these are matrices. So basically the 0 matrix. Okay, so evaluating a matrix, evaluating a polynomial at a matrix, understand. So why is this happening? Why is there a polynomial Px? Maybe non-zero polynomial. Zero polynomial is obviously there. Why is there a non-zero polynomial? Well, that is very simple. Right? That is simple because that follows because of the dimension. Right? So you know that dimension of MNF. So MNF and its dimension. Dimension we mean as a vector space. The MNF is also a vector space over F. Right? The matrices also form a vector space under addition. Here the multiplication structure plays no role. When talking about the dimension, the multiplication structure plays no role. Okay? If anything is not clear here, you should tell me first. We have discussed dimension, so that's why I'm using the word. You know that the dimension is equal to n square. Okay. N square, which means that any collection of n square matrices is going to be linearly dependent. Right? Any set of size n square plus 1 is linearly dependent. This implies that any set of size greater than n is dependent, right? Because it means basis is the size n square and so on and so on. So this gives us a hint. What is the hint? The hint is to simply consider a square and this. So these are already n square plus 1 thing. and so they will be linearly dependent. So this is a linearly dependent set. Is linearly dependent. Okay.
So what if these we don't have n squared elements? Like what if a squared is equal to a to the power 5 or something like that?
That's a
Or
good
something like
question.
that.
Yeah, that's a good question. So in that case, uh, yeah, that's a good question because there may not be n square distinct elements. So in that case, you are getting that there is some a to the power k plus 1, which is equal to a to the power k, or not that actually, a to the power some s, which has come previously, right? It could be like this, or it could be 0. But in that case, you already have a polynomial relation, right? X to the power k plus 1 is a polynomial that will work, or s to the power k plus 1 equal to x to the power s, correct? So you will get a polynomial.
Okay, yes,
Yeah,
yes,
but you are right. I mean, that case needs to be
yes.
considered, otherwise the proof is wrong. Yeah, that's otherwise it's not correct. It's linearly dependent. And from here, I suppose you can complete the just use the definition of linearly dependent, and you have obviously a lot of these CNs, lot of these CIs may be 0, but the only condition is that all of them should not be 0. Okay. And so you get a polynomial, right? So the polynomial is T naught plus T1x plus Tn x to the power n square. This is it. Okay. So we want to actually make it better. We want to show that there exists a polynomial Px of degree at most n. Because this is too high, and so that's why it's easy. But we want to get a polynomial of degree at most n, which does show. And that is an interesting thing. That's where algebra and vector space come into play. Because even though this is the n square dimension vector space, these vectors a square, these are sort of related to each other. Algebraic sense, they are related, right? Because they are powers of one thing. That's why you don't get n square. You don't have to go beyond n actually to get a relation. And that is a claim. That is not. Is it obvious? I don't know. Yeah. So that is the Cayley-Hamilton theorem, and I will just talk about it a little bit because I have said that in the last class. But yeah, and then we will want to talk about prove some generalizations. So just hold up 1 minute. I will just come. Yeah, and then we'll Okay. First time erasing this. Let me know what's on.
Yes, sir.
In a way, this is like the starting point of linear algebra. Interesting thing. Of linear algebra, not of vectors, but of collection of maps between vectors. And A is a function, right, between vector spaces. But we will not need that viewpoint right now, so I don't want to mix up everything. And this is, as I said, Cayley Hamilton. So, Cayley and Hamilton, you should read about them, different mathematicians. History is the interesting history about this theorem, how this came about. So you could read the Wikipedia article. But I want to talk about this through a more general picture. So I want to talk about what is called the multivariable Cayley-Hamilton theorem, about which I know very little. So yeah, that's why I want to talk about it, so that I can understand it better. And obviously, from here you will also understand Cayley-Hamilton. It's a special case. Cayley-Hamilton will become a special case, will not lose anything. Yeah. So look at this viewpoint. Multivariable Cayley-Hamilton. Cayley-Hamilton theorem is, I think, you should check. You should read and tell me. Okay? It's somewhere in 1800s, later side of 1800s, I suppose. And the multivariable Cayley-Hamilton theorem apparently comes up in 1900 something. Okay, it's in a paper. There is a paper called "Functions of Matrices" by H.B. Phillips, which is from where I'm taking. So you can have a look at it if you like. But this is not a primary homework for anything. It's Functions of Matrices by Phillips, H.B. Phillips, and yeah. In this paper, the functions of matrices. And 1919, and then continuously work has been done. Okay, so I attended a conference in just recently, Pondicherry, and there some new work is being done in this. So they generalize this multivariable version also, and more than that, the exact generalization, in fact, I don't know, but they gave a proof using combinatorics, using paths and walks and some bijections and things like that. Okay. And that's some remarkable thing. And the paper was published, 2023 was the last paper actually, just 2023 only, by some people from ISC, and many people have worked on it. So it has been going on. But obviously, we'll do a very basic version of this. Yeah, but this paper one can read. The only difficulty in reading this paper is the language is a bit old, so they don't say field, they say numbers. And then you have to think this number belongs to which set, number system. Is there some slight confusion in that line? But what does it say? So it is saying that let, or maybe I will use some better language, better notation. Let A2 this thing till AN be in MNR. Okay. And again, another, so now we are looking at collections of matrices. This is also in MNR, but more interesting. be a commuting family. Okay, so commuting means that these matrices, the lower row, they commute with each other. Be a commuting family. Okay. So if there is a system of equation, if there is a just a one, if there is a linear homogeneous equation of matrices with coefficients also in matrices, so you can see what is happening. The analogy of this with usually these are all numbers, and so you can think of, okay, if I'm wrong, then see, you can think of these a1 prime, a2 prime, and an prime maybe as variables, and these as coefficients, but everything is now coming from matrices, not from numbers. Okay. This commuting is sort of important. You will see. If this is equal to 0, then there is a polynomial relation, but there should be something more. Because they will also yes, yeah, otherwise what's the meaning? Sorry, yeah. Then you consider this polynomial. Yeah, otherwise, yeah, always remember that if you're talking about some polynomial relation between matrices, there has to be some condition on the polynomial. Otherwise, there are always polynomial relations. If you go high enough degree, then there will be a polynomial relation. But then that kind of statement is not a theorem. That's a trivial. But some specific polynomial will do the job is really the important thing. And in this case also, this is half of the statement, right? This I've said degree at most 10, but you know that the polynomial is actually this determinant polynomial, right? A minus xi. This polynomial, determinant of a minus xi, x is a free variable, and this is a polynomial in x, and that polynomial works. That is the thing, and the degree n comes, yeah, I want to state it repetitively. So in this case also, you look at this polynomial, which is obviously now is going to be multivariable. So you look at this polynomial, and these are all variables. Okay, x1, but plus the determinant. So determinant x2 is a just free variable. It has no connection with anything. Again, those things can be formally described, but you understand. The determinant of this, write the then later. You look at this polynomial now, which is an n variable polynomial. Okay. So this lives in, should stop writing R. The reals are not important. It's just that you need a place where you can divide, multiply. So reals, you don't need to be real. Okay. So they are in F. Okay. Right. Yeah. They are just polynomial in variables, 0, and then okay, P of a1 prime, a2 prime, an prime is equal. So how is it making sense? We will see how Cayley-Hamilton theorem comes from here without proving it. But please tell me.
Yes, sir, it makes sense.
Makes sense, right? So what?
Yes, sir.
Right. So from here, one sort of principle which you can derive, which maybe you can use to predict or put other theorems under that umbrella, is look at these two. Okay? So number one is saying that this a1 prime up to an prime are linearly dependent, where this dependency, the coefficients are coming from matrices. A1 prime up to an prime are a system, are a solution of a linear homogeneous equation. Okay, so that linearity is a very nice thing. Okay, but the problem is that the coefficients are coming from a like it's coming from matrices, not coming from a commutative ring, not coming from a commutative thing. A1 and an are matrices, and the biggest problem with that is that they are non-commutative, not because they are matrices, but they are non-commutative, right? That's the thing, and they are not invertible also. So that's another thing if you like. That's a problem. But the good thing here is linear. But you look at equation 2, this is also about a relation. A1 prime up to an prime are related. And where are the coefficients now? The coefficients are now from a field. They are no more from matrices, right? The coefficients, because P is a polynomial, the coefficients are coming from a field. But now we have to raise to degrees, right? So now the linearity, in that sense, the complexity has increased. But in some sense, the complexity has decreased because now we are in a the determinant is their intermediate
And
part.
that's happening because we're taking the determinant.
Yes, that's what I was doing.
Yes.
Right.
Yes, sir.
Yeah. So it's solving, it's a trade-off. It was always the case. For us, there are two goals. One is to prove this result, okay, and second is to understand how the Cayley-Hamilton theorem comes from this theorem. These two are supposed to be, I think, the goals. Okay. I mean, the proof is not difficult, but let's at least see how this comes. Maybe can omit the proof in the first thing, but at least we should see how. So if you want to prove Cayley-Hamilton theorem from this multivariable Cayley-Hamilton, okay, I should not have erased anything, but anyway, so this will be a quick thing here. If you want to prove this Cayley-Hamilton theorem from this theorem, so what should you take as n? That should be the first question. Okay, another mistake. So, we don't have n, this is just m. This doesn't depend on that. Of course. I suppose, yeah, because usually it works for, you could have more than n also. If it's less than n, then it is fine. You can take the rest to be 0, but pad it with zeros, but good. So what should you take as your n? You want to prove this. Again, you see Cayley-Hamilton theorem, you can see that it is similar, but what should you take as m? So I'll take m as 2 obviously. Okay, take m as 2, and this a1 prime and a2 prime you have to choose, right? And a1 and a2 you have. So I suppose it's not a surprise. You choose your or maybe a1 is easy to choose. So what should you choose as your a1? Yeah, because just look at this determinant and then it should be clear. You choose a1 as a, and what should you choose as a2? Minus I. Right? And then if you look at this thing, then it will be clear what to choose as a1 prime and a2 prime. A1 prime maybe choose as whatever, I or minus I, and this as. Then you can see that it happened. Or maybe, I'm sorry, I think plus. You can see one is satisfied. equation 1, and they commute because identity commutes with them. Okay, and then this theorem tells you that if you look at this thing,
Sir, I don't understand why we took MS2 because if MS2, then we'll get a polynomial in two variables.
right, exactly, correct. That's a good thing. But if you take n as 1, then it's difficult to prove anything also, right?
Okay,
Given the
okay.
nature of this
Yes,
equation, yeah. So you will get a
it's
polynomial in
tough
two
to
variables,
choose.
right? It's not. It's because Cayley-Hamilton theorem is stated in a bad way usually. I would say it's like that. Actually, it's a two-variable polynomial, but the y is put equal to 1 usually, and that's
Okay,
how it.
okay,
And
okay.
that's why we don't get the
Ah,
picture. Now you get it.
right, right.
That's all.
Yes.
And so you just have that ax. So this is a1x minus I. This is a polynomial which is satisfied. So here in this polynomial, uh, a1 prime, one, right? Yeah. So now this is the by the theorem. This is the situation. And now what can we say? We know that p of I, comma a is equal to 0.
So now we can just take g of x as p of I comma x, and that'll be our the what we were looking for, like in the original Cayley Hamilton.
Yes. No, but okay, okay. No, but there's a problem that I you cannot just ignore in that way because yeah, there is some. Uh, maybe you're right. P of I comma a, and then you can take if you take this as probably that is correct. What you similar to what you're saying. Just take this as q of a, right? And then you will see that this q of x will actually be equal to this x1 is actually put equal to 1. This
Yes,
one,
yes, so that's what I was saying.
that's what you will see. And that's it's pretty clear, right? Because wherever I is coming, so suppose let's just take a quick example. It's good to take example. Suppose it is whatever. So some square x2 and 2 or whatever x1 plus x2 square. Yeah, it will be homogeneous. It will be a homogeneous polynomial if you consider x1 and x2 both. It will be homogeneous because the determinant going around. But all that is fine. You take this and then you are putting I and A, right? When you put I, then because I is an identity, right? And then you put A here, you actually put it. So it will be 2. I mean, it's clear, but I'm just saying. So 2IA plus 2A square, and then you just ignore the I. And ignoring the I is just putting x1 equal to 1. Okay. And I could have not said that earlier. Yeah. It's happening because of I. Okay. Yeah. That's just putting x1 equal to 1. And then you understand. So this is a generalization of Cayley-Hamilton. It's indeed multivariable Cayley-Hamilton. Actually, it took me some time to see that actually, when I was reading. But yeah, it's good that you people can see it directly when you're at least faster than me. That is important. I mean, yeah, because I mean, I was not being directed, right? Reading on my own. That took me some time, but it should not. But yeah, anyway. In the end, it's simple. And so in the end, if it is simple, then there is a scope to understand it fast. And that scope is important to get. Take that. Okay. So, I mean, now the proof of this is not difficult, but maybe we can omit it. But now, within these 2 minutes that are left, I would like to state the Cayley-Hamilton theorem is another generalization, which is called Nakayama lemma. Okay, and both the proofs, all the proofs are done in a similar way. Okay? But I'll state that. Let me state. It's called Nakayama lemma. This also proves the Cayley-Hamilton. Proof we can talk about once later. So what is this saying? So this is saying that look at a module over a ring. Module over a ring, and this is nothing. N. So it's a commutative ring. Okay. So maybe I will omit it. And after the break, we will do something else because there's not much. Okay. But we will say it at one point. We'll see. Let's take a break. Let's take a 5 minute break.
Yes, sir.
Because I also want to do
Yes.
one problem from IIT Jam. This one more. Move on. Let's see.
Yes, sir.
But one thing I'll just say is that the key to these proofs, obviously there are some long computational proofs, but the key to proof, I gave one proof last time using some analysis, topology and analysis, density, assumption set, so on. But the key to proving these things nicely is to expand our viewpoint. And the expanding viewpoint means that usually we look at matrices with coefficients coming from a field, but then to expand the viewpoint and start to look at matrices whose coefficients, whose entries are also matrices, but commuting matrices. That is, if you start to view matrices whose entries are matrices, then all these proofs become very simple.
So that commuting is like we're sort of imitating a field,
Yes,
but we
yes,
still want to keep the matrices.
yes, it's imitating a field without inversion, so it's a commutative ring. Yeah, good.
Yes, yes, sir.
That makes the proof. Okay, thank you. So I will meet after 5 minutes.